Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 3, Lesson 5. We are going to learn today about a device called a capacitor. A capacitor, that's an O, C-A-P-A-C-I-T-O-R. Let's start by just looking at this word capacitor. To me, it sounds like the word capacity. And when I hear the word capacity, there's several different things that could mean. But one thing we say is we could talk about a vessel that holds liquid. Yum. Herbal tea. We could talk about a vessel that holds liquid, and we could say its capacity is about a cup and a half. So when I'm talking about a thing that holds liquid, what I really mean is its volume. So sometimes capacity would be a volume. Now, other times you'll be in, not so much in a home, but in a public building like a classroom, there'll often be a sign over the door that says something like maximum capacity. And it's not talking about the volume of the room. Are you anticipating what I'm going to say? It'll say something like maximum capacity 50 people. And so if you can't have more than 50 people in that room. So, how much it can hold, either how much liquid it can hold or how many people it can hold. And then maybe you'll think about, oh, but I've seen capacity signs over doors that say different numbers. So sometimes if you're in a hotel or an office building, the capacity sign will say something like capacity 50 people for a meeting, but 30 people for dining. Usually the number of people that are allowed in a room when there's food involved is smaller than the number of people that are allowed in the room if they're just going to be, there without food. So sometimes capacity is situational. It depends on what's happening. So that's what pops into my head when I hear the word capacity, which does relate to this word capacitor. Now, let me make it a little bit more sciencey. What if we're going to play volleyball? So the volleyball has this little place here where I can pump it up, right? We have our we pump the volleyball up with air. So when I'm going to put air into the volleyball, I can't remember, how much air is supposed to go into volleyball to make it regulation, but I pump the volleyball up, and it's full. The volleyball, cannot expand anymore, so it's full of air. But could I pump more air into it? Yes, I could, and the volleyball would get harder, right? And then could I pump more air into it? Yeah, I could pump more air into it. So the amount of air that's in there is like its capacity, but the amount of air depends on another variable, right? We would call the amount of air, N, the number of moles of air. But that number of moles, because we recently talked about this, depends on the pressure. So it can hold more moles at a higher pressure, and it can hold less moles at a lower pressure. That's kind of like a room in a hotel that can accommodate some number of people under dining conditions and another number of people in meeting conditions. So having put all that together, capacity is sometimes just one number. What's the volume? But sometimes it's a number that's different depending on the situation or the condition. So a capacitor is a thing that holds stuff. I'm going to tell you what the thing looks like and what kind of stuff it holds. But the amount of stuff it holds is not always the same. It can hold a certain amount of stuff under one condition and another amount of stuff under another condition. So that's the kind of story I'm about to tell. So I am going to tell you a story. I'm going to say, what if I have, a sheet? Maybe it's a sheet of metal, maybe it's a sheet of paper, and another sheet. and they're near each other. Now, I want to make them look like they're parallel to each other. So I'm going to draw them three-dimensionally. So it is a flat sheet, but I'm drawing them like this so that they look like they're held parallel to each other. So what I'm trying to show you is two sheets held like this. See, like this, parallel to each other. So that's what I'm trying to draw. Maybe they're sheets of foil. And what I'm going to do is I'm going to stick a wire on the end of one, and I'm going to stick a wire on the end of the other one, and I'm going to connect them with a battery. So the batteries have this little dot on the positive end. So now I have these two sheets that are connected with a battery. And what this battery tries to do is it tries to make current flow this way. I is the letter we use for current. But of course, positive charges don't flow. Positive charges are trapped in the nucleus. So negative charges, which are out there in the electron cloud, are more free to move. So what this is going to do, if I want current or positive charge to flow this way, what's really happening is that electrons are flowing that way. So I'm going to rip electrons off of here, send them through the battery, and stuff them on over here. So when I rip an electron off, that leaves, there was a plus and a minus together. I removed the electron, and that leaves this unpaired positive. So when I remove an electron, this thing becomes positively charged. And the electron comes over here, and it gets put on that plate. Okay, I'm telling you a story. Now, this is still pulling electrons and trying to push electrons over here. So I'm going to pull another electron off. The question is it the same, or is it easier, or is it harder to pull the second electron off than it was to pull the first one off? Well, I think it's going to be harder to pull the second electron off, because if I have an electron here and I'm trying to pull it away, this positive charge is pulling it back. And when I'm trying to take this electron over here and stuff it on here, this electron is repelling it, pushing it back. So it's harder to remove the second electron. And then it's harder still to remove the third electron. So it gets harder and harder and harder to do this. So the amount of current, decreases as time goes by. And eventually it just gets impossible for me to pull any more off using this battery. So that is the story. Eventually, no more get pulled off. And we say that this is full of positive charge. This is full of negative charge, full. No more is going to happen. And this is full of positive charge. And so that full, my cup is full of yummy herbal tea. And this plate is full of negative charge, and this plate is full of positive charge. That's what we mean by full, what its capacity is. So these two plates are a capacitor. Two parallel plates are a capacitor. That is the thing that is a capacitor. And it has a capacity, the amount of charge that I can move. Now, some of you might be thinking very strategically, you might be thinking, hey, if this is 3 coulombs of charge, then this is negative 3 coulombs of charge. The magnitude of the charge here, it's positive, and the magnitude of the charge here that's negative will be the same. So what do I mean when I say how much charge? You might say, plus 3 and negative 3 adds up to 0. That's not what we mean, but I can see why you would think that. Or you might say, oh, well, we'll just take the absolute value. So 3 plus 3 is 6. You might think that, and that's very rational to think that, but that's not what we mean. When I talk about Q, the amount of charge stored on a capacitor, in this picture, Q is 3 coulombs. So the amount of positive charge on one plate will always be the same as the amount of negative charge on the other plate. And whatever the absolute value of the charge on either plate is, that is what we mean when we say Q, the amount of charge on the capacitor. So now I say, okay, so if this happened, this was 3 coulombs. And if, I move, there's positive 3 coulombs here, negative 3 coulombs here, the current has stopped. And let's say that this was a 9-volt battery. Well, I'm not just going to say the capacity is 3 coulombs, because if I changed this to an 18-volt battery, then all of a sudden more current would flow. Oh, if I change this to a 6-volt battery, current would go back. 6 volts wouldn't be enough. So the way this is set up, I've got 3 coulombs per 9 volts. So the capacity, or what we call the capacitance, C-A-P-A-C-I-T-A-N-C-E, it is a capacitor that has a capacity, but in this context, we call that capacity capacitance. The capacitor has a capacitance. It's 1/3. 3/9 is 1/3 coulombs per volt. For every volt that the battery has, I can move 1/3 of a coulomb of charge. Now, I just made up the numbers. But in this situation, the capacitance of this capacitor is 1/3 of a coulomb per volt. So a capacitor is measured by its capacitance, and the unit for capacitance is coulombs per volt. Now, of course, that makes sense. It's what's going on. And when things make sense and they tell us what's going on, we tend to pick some white guy from the past and use his name instead. So we call a coulomb per volt a farad, capital F, named after Michael Faraday. I don't know why. It takes, I wish we didn't do that. So the physics is that capacitance is measured in coulombs per volt. And then in the real world, they don't call it coulombs per volt. They call it farads. Sorry. So that's what a capacitor is. It's a way that we can store or separate charge. All righty. Now, you might be wondering, well, what is it that determines how much charge can move from one plate to the other? And it turns out that there are a number of factors. So C, the capacitance, is a measure of how much charge can move divided by the potential difference created by the battery. I forgot to draw the battery, sorry. But capacitance is also determined by the area. If this plate has an area A and this plate has an area A, I say that the area of the capacitor is A, not 2A. It's just A. So the capacitance is greater if there's more area. There's more charges that I could pull on, and there's more space to store the charges over here for them to spread out. So more area, more capacitance. I can move more charge. And it turns out that this distance between them also matters. It goes in the denominator. The way I think about it is if I have plus charges over here and minus charges over here, as I rip another electron off and try to shove it on over here, these guys are going to repel it. But if this D gets smaller, then these pluses are going to attract this negative charge. So if they're closer together, there will be less repulsion, or there will be the same amount of repulsion, but there will also be some attraction mitigating that. So smaller D, more capacitance, greater area, more capacitance. And then we just need a proportionality constant, because the unit for capacitance is coulombs per volt. But this is square meters over meters. So this is just meters. So I need a proportionality constant to change the unit. And that proportionality constant is epsilon naught. Look in your book for what number that is. So this is one way of thinking about capacitance. It is how much charge per volt. And this is how I build my capacitor. I make a capacitor have more capacitance with more area. And so sometimes I could put these equations together and get Q over V equals epsilon naught A over D. And it turns out that you're going to use that equation to solve some problems as well. All righty. So I just want to point out a couple things. Look at how I said capacitance, and then in parentheses, I said its unit. Coulombs per volt. And then here I said capacitance, Q is the abbreviation for charge. Coulombs is the unit for charge. Q is the abbreviation for charge. Unit, abbreviation, they're different things. And then look at this. This V is the unit volts. This V is the quantity voltage or potential difference. That's hard to understand because we use the same letter to mean those two different things. So just be careful about that. This C is the unit coulombs. This C is the quantity capacitance. Oh my goodness. So I use capital C to mean two different things. This C does not mean capacitance. This C is the unit coulombs. This V is the unit volts. This C is the quantity capacitance. So it would probably be a good idea for you to continue this piece of paper that I started for you in the previous video. So I'm flipping through my pages to get the piece of paper that I started on. Remember this piece of paper from the previous video? I said there's electric field and electric potential. These are their abbreviations. These are their units. So now there is charge, has the abbreviation Q and the unit coulombs. And then there's, I'm going to squeeze it in here, capacitance has the abbreviation C and the unit for capacitance, coulombs per volt or farads. So these C's all mean coulombs because this column is units. This C means capacitance, abbreviation in this column, unit in this column. These are quantities in this column. Quantities, abbreviations, units. Abbreviations are different from units. The abbreviation for mass is M. The unit for mass is the kilogram. Okay? Final thing. I drew this lovely three-dimensional picture, but the capacitor and the battery are often drawn as symbols. So I draw a capacitor with just two parallel line segments like that. And then I connect it to some wires. And then instead of drawing a three-dimensional battery, I draw a battery as two parallel line segments. So two parallel line segments capacitor, two parallel line segments battery. The longer segment is the positive end of the battery. Oh, a capacitor doesn't have a longer segment. So two segments of the same length is a capacitor. Two segments of unequal length is a battery. So make sure they look really unequal length. And I don't have to put the plus here because that's redundant. The longer segment is the positive end. So this is the positive end. This is the negative end of the battery. And this is a capacitor. It's a symbol for a capacitor. And this is the symbol for a battery. They look very similar. They're both two parallel line segments. If they're the same length, it means it's a capacitor. If they're different lengths, it means it's a battery. That's all I have for you. Have a wonderful day and be very careful not to break any of the laws of physics.